thank you, Pepe. So when we speak about finding new materials, it's of course we know that materials are really important. They are crucial for many of the most pressing challenges we have. We want to innovate there, find new compounds. That's the reason we are all here in the end, also in FAIRmat. But in the end, when we think about this, we often compare it to finding a needle in a haystack. And of course, in our case, the needle is the optimum compound in the space, in the space of all the possible materials in there. And so people over time went into haystacks looking for needles, but interestingly, none of them has been using ML to do so. They somehow already do this by hand manually. So the question is, I'm here to speak about using ML to help us in materials discovery. So why do I think I can do this when they somehow didn't use machine learning? And this might seem like a not reasonable question to ask, a somewhat funny, not serious question, but I think that going through this can really help us to showcase what the challenges are in doing this, but also what the promise is of doing this with machine learning. So when you think about looking for a needle in a haystack, your challenge is quite simple. You look for this one needle in this haystack, you have one objective, and once you found a needle, you're done. So it's quite easy to do it. But if you look for material, you have to find different kinds of things. You have a high conversion, should be selective, scalable, efficient, perhaps even cheap and safe. So you have to satisfy all of those different objectives. And in the end, if you don't know a priori what the weight between those different things are, you no longer have a nice ranking between solutions. But the best you can do is that you can have a set or two sets. One is the set of the good materials, which we call video optimal, and then the set of the bad ones, which are here in orange, which are dominated by the green ones. Because if you don't have any weights on the objective, you no longer have a total order, no longer a line to compare stuff along which, but you can only say those are better because I cannot improve this green point here, for instance, or like this green point here without losing performance in my objective here. So this makes search way hard because you no longer have like one nice line to rank stuff along. But it gets even worse because we have to look at, of course, different scales. You might have a perfect catalyst on the atom scale. You have a perfect active site. NERSC could give you a scaling relation for the atom site. But then you put it into a pore, into a zeolite, into a MOF, and you find that in the end, in there, nothing happens. Because if you have no mass transport, of course, there will be no conversion. So you have to look at different scales. You have to have the good atom scale, but also the right pore scale, for instance, to have the fusion there to the active site. So looking at only one scale won't help you. This again makes search way harder for you to do. And then in the end, we are also spoiled for choice. We just have too many options to go through. I mean, it's what all of us basically say in our papers, I think. Material space is big. You have different estimates how large chemical space is. This is one I like because it's a large number, where you look at how many ways you have to fill this box with atoms. Of course, many things in there won't make sense. But in the end, this is just the atom scale. And you have to still go through microscale and so forth up to the device level in the end. And there's just too much to go through by hand to just brute force it. And if you were in a haystack, the best you can do is to just do random search, because there's no structure in a haystack. So the best you can do is to just go randomly through it, and you can learn nothing on your path through this haystack so far. But if you are in chemical space, you can start taking measurements and data simulations and build a map of chemical space and get more and more contours, more and more color, and see where the interesting parts of this chemical space are. And let this map then guide you to the interesting parts, which might be easy to capture or some other things. And of course, in the end, models are what can capture those maps. They can basically learn to map coordinates in the space to then what the performance is in different parts of this chemical space. So we want to use models to learn those maps of chemical space, but models can learn almost anything. So if you have a neural net that's sufficiently wide, it can learn any function. We want to only learn the right functions, so only a small part of all the functions. So how do you now go from all to the right functions, from the black part to the red one here? And so one way, if you're Google, is that you just use data. You just throw all data you find in there, and this way constrain what you can learn with data. And if you have more data, of course, have less function. It can be described in this way. But if you're in chemistry, we all have only small data sets, quite diverse ones, quite noisy ones. So we have to be more clever in this case and add all we know about chemistry and physics as prior knowledge, as inductive biases into our models. And so what I will show you next is basically exploiting those two ellipses, getting more data, linking data, but also putting more physics, more chemistry into our models using those inductive biases to, in the end, go from blank all functions to the right functions, hopefully. And so for this, we have been developing, of course, a tool stack. In the end, I believe that science is tool-driven. I think this is something you also share. To some extent here, we have infrastructure for getting data in a consistent form to then go from structures to vectors you can put into a model. This is a really important part because it's not a trivial thing to do because you have different number of atoms here, different types of atoms, and you often have to go to a fixed length vector. So there are many things you can do here, and to also improve the model, add more physics in there. And then you also have to somehow see if the model makes sense. You also have to somehow measure performance of the model. This is, again, nothing that's too easy. It sounds easy. You can just use a mean absolute error, but this often isn't the right metric to use. And then once you have a good model, you can then use it to guide you through chemical space, using this as a compass, as a guidance through this map. And over time, we have been using this across scales, from the atom scale over the mesoscale with polymers up to then even the plant scale, where we look at emissions of a pilot plant. And in all of those cases, a common thing is that just theory alone doesn't help us in those problems. So if you go to the pilot plant here, for example, you look at emissions of those solvents that capture CO2 in this plant, and we have no theory at all that can describe how those emissions behave as a function of how the plant operates. And so the best you can do there is you can just use data and then try to learn from the data how the emissions behave as a function of the behavior of the plant. And the same holds true like at the atom scale, the oxidation states. Again, it's important, but we have no physics that is an operator that can give us like what the oxidation states should be. So the best we can do is to learn from data in this case. And this, I think, is really the common theme here to address complexity using a data-driven approach. And so we will use this compass theme, and then I want to drill on two different ways of building those models with different kinds of inductive biases. One will be this perhaps old-fashioned or conventional inductive bias with feature vectors, where we basically can put physics in there in the way we constrain and construct those feature vectors. And then perhaps a novel way of doing this using LLMs, which also have inductive bias, but they are quite different from the ones that those old techniques have. So let's start with using this search theme. Let's see how we can use the models to guide us through chemical space. And with this, we work with BASF, and they have a problem because they want to make money, and they make a lot of money with dispersants. And dispersants are things you put into solutions of pigments to keep them color bright, for cars, for instance, for a car paint you have in there. And they can make many polymers. So they have many polymers they could make in their labs at BASF. So they have this huge space of monomers they can link together in some way. And I want to know now which are the ones that are interesting for us to look at, to focus our attention on, because we could not just try all of them. It doesn't scale. So we want in the end have a way to focus your attention on the ones that are probably promising, and you have different kinds of objectives for different customers. And those are that probably you can just throw away because they will be bad for all customers in the end. So you want to have an efficient way to filter into those two classes, into the good ones and the bad ones, and also want to avoid you miss one of the best polymers in the space. You want to be confident in doing this search through chemical space. So you have those three objectives here. You want to make this thing stick to a surface of a pigment, repel other dispersants, and then in the end be not too viscous to make it easy to use in solution in the end. Trying this all out in the lab doesn't work, but luckily we have a friend there that has simulation workflows for this. So it gives us numbers like absorption energies and the rate of gyration. But in the end, even though Brian was really efficient in making those go fast, but it still takes a week or so per polymer in there. So it still doesn't scale to all the polymers you can come up with in this space. So what do we do now? So how do we address this mess that we have here of different polymers? So the first thing you might think of is that you can just replace this cheap, this expensive molecular simulation with something cheaper. And of course, cheaper for us is using is using machine learning. So we have to somehow go from our polymer monomer sequence to then the numbers in the end that is our labels you want to predict. But the question is now, how do you now build this model to make it in the end efficient and confident in what it does? And for this, I think there are two extremes. One extreme is to just throw all the data in there that you have. In this way, you have a perfect model because it has seen everything, but you didn't win anything in efficiency because you have to still do all simulations in the end. So this doesn't help you that much. The other extreme is to just use some polymers from the space. And this way, you're way more efficient. But in the end, can you trust your model? It's still unclear. So we'd like to have somehow a feedback loop from the model and telling you what the next best thing to do is. So we'd like to have this closed loop where a model tells you this is the next best thing where I can learn the most from in the space. So the challenge is now that we have those different objectives. We have the adsorption energies, the radius of curvature, and so how do we now bring them all together in this optimization? And you might think you can just add them all up. This is something people commonly do. They just like take a linear sum of objectives with some weights. Depending on the weights, you find different points here in this objective surface. And you can try out different weights, and you'll find different points here in this objective surface. But if you have a real-world problem, your surface might look like this. You have this non-convex area. You could try different weights here, and you will never find any point in this non-convex part here. And it's just to say that searching in multi-objective spaces is quite tricky. And if you don't know a priori what you're doing, what the weight should be, this is a mess to do. So what do we do now? So how do we avoid adding any weights, doing any kind of featureization or combination of objectives to still search in the space here? So I think the solution here is to just rely on divide and conquer. So in this case, we have in this space every point here being a polymer. We just look now at 2 objectives, but of course you can do this with n objectives as you want. And then we have a model that can tell us uncertainties and the means. The means are just the positions here of those points here, and then uncertainties are those rectangles. And so you have uncertainty in objective 2 going up here and objective 1 in this direction here. And then there's something interesting you can do it because if you want to maximize both of them, the best case is that if you're here at the upper bound. So this is the best case for maximization because then you have the highest possible value for both objectives here for maximizing thing. And the worst case, if you have the lower bound here, where you're here. And you see some of the points here, the best case is below the worst case of some other points. So in this case, if you look at this one here, for instance, here the worst case here is above the best case of all of those red points here. So know for sure directly from quite early on that you can throw away many points in the space here because you know for sure, because you have uncertainties here, that you can throw away all the red points here. You know then that the green points are interesting, and then the next best thing to do is to reduce uncertainty in this gray area. You take a new sample there and retrain a model, and then you're quite quickly done. You see this, for instance, here, where you compare to just this random brute force needle and haystack approach. Is a measure of how well we do. We want to minimize the error, of course. Orange is just brute force random search, and we have a log scale of how often we call simulations here on the x-axis. And then we can be way faster, of course, with this approach. And an interesting part is we can tune how fast we go by tuning how we scale those rectangles. You can derive error bounds. And if you have good uncertainties of your model, you can derive that if you scale those rectangles here in a certain way, you will have a certain probability all solutions in the output. And in this way, you can tune and trade off between going fast and finding all solutions in the space with some confidence in doing this. And this, in the end, has been used not only by for materials discovery, but also for different applications like process optimization, where you always have the same thing, that you have to balance different objectives and want to find the interesting solutions in the space efficiently and with confidence. And the key part in there was the model that can somehow map the monomer sequence to the properties of the polymer in the end. So I want to dig deeper a bit into how we build models, and for this go to the atom scale. At the atom scale, we have something quite important for chemists, the oxidation states. It's in the name of the compounds. Chemists talk about this all the time, but there's no theory behind it. So there's no operator quantum mechanics that can give you oxidation states. There's no physics that can really measure oxidation states. It's all in the end just some assignment process. Also, if you do XPS, it's just some assignment based on some rules that you just came up with at some point. But still very important. So chemists developed rules like even Pauling developed something at some point called the bond valence technique, where you have an exponential of the bond length of the different bonds around the center and then add them up. And then you can tell if it's like copper 1, copper 2, copper 3, you name it. And if you do this on some copper cases, for instance, you see that Pauling, which is shown here in red, doesn't do much better than just saying always copper 2, which isn't that satisfying. Because if you're a chemist, in the end, if I show you a compound, you're quite sure what the oxidation state is because you have intuition, given the shape of the environment, what the oxidation state will be. And so the question is now, how can you now leverage this intuition of chemists to build better models? Because in the end, if you run a DFT, for instance, you want to know what the oxidation state is to assign then electron counts on your metals for DFT simulations, for instance. So how do you now make this scalable, what chemists can do just all the time without any efforts? And for this, we just rely on assignments of chemists and rely on features that chemists would also use, perhaps. So we have now here locality assumption. We will focus on local environments, like on local copper environments like this one here. And then for each environment, we have a vector that tells us, of course, what the middle element is here, but what the metal here is, what the elements around this metal are, the local chemistry around this metal, and also, importantly, what the shape of this environment is. We have vectors describing what the shape is, how square it is, how planar it is, how tetrahedral it is. So we have those shape descriptors for each environment in there. And so we derive for each atom those 100 numbers or so, and in the end, we go to the CSD, where we have tens of thousands of structures, and in there we have, in the names of the compounds, the oxidation states in Roman numbers. And they might come from intuition of chemists, might come from XPS, something else. We just take all of them. We featureize all the atom size. We have this feature vector in the end. And so as chemists have different ways of assigning those numbers, we have different models, which all have their own way of reasoning, of course, have different votes of different models. And in the end, in this way, we get an ensemble vote in the end, which will be a final prediction. And of course, it's all open source. There's also an API for this, and we use it in our DFT workflows to initialize the electron counts of our MOFs, for instance, because that's often a challenge to know if it's copper 1 or 2, because you have to initialize the electron count to do a DFT simulation there. And therefore, it's really important to have those things in place. And so let's see how this works in practice. So here we have so-called confusion matrices, where we have here the actual oxidation states against predictions here. And we'd like to have everything in blue, in the ideal case, on the diagonal. And we still do quite well, but if we now add those voting steps in there, look at when all models say the same thing, we do even better, and we have everything even more blue on the diagonal. And if you go back to compare to Pauling, we again do better than Pauling here. So we have here different ways of telling how good we do. For copper here, where we have an optimized way of this bond-Weinstein technique, and we do much better here. But the even more interesting thing is if you go back to the CSD and look where your model is quite sure, but still say something else than what is in the CSD, you can find the list of tables, of table after table in our SI with typos we find this way. Because if the model is really sure, but the CSD is wrong, quite often there was a typo like flipping 4 with 6 in Roman numbers, which we found in this way with those models. So models can really help you also then curate data and be a sidekick for chemists to make them the data more clean, for instance. So this, in the end, all relied on data. And if you do ML, I think all of us then know that we don't have enough clean data. We would like to always have some more clean data. And so another key part of my work has been looking at how we can get more of data that's in the end usable for us for building models. And so for this, I have been working a lot with Luc Patini, who has been developing an ELN, EPFL, and we have been customizing this a bit more for the challenge we have with MOFs, for instance. And so what's the idea in here? The idea is that having data in a structured form is really nice to have, because if you, for instance, want to do pancakes, you go on Google, you can just search there for pancakes, and in the end, what you get here are nice comparisons of different recipes in this nice table here. They come from different blog posts, different websites, but in the end, they all appear in the same form here. They all have the ingredients here, the ratings, even though they come from quite different blog posts and different websites in here. And in the end, if we are in a lab, we also have recipes in there. So why don't we have something like this in chemistry to also look for recipes in a chemistry kitchen, in a lab, in the same way. And this works in the end because if you have those pancakes, like if you have Kevin's quick recipes or Baron's recipes, in the end you have some structured form in the HTML of the blog post, for instance. So it's schema.org, where you have all the information in some structured form with shared vocabularies, for instance, in there. And if you would have this, you could hopefully then think of envisioning something like finding all the moths that you can make in water. I mean, this is even more tricky because you have to do semantic search, but you can in this way envision a way where you can also look for recipes in chemistry in the same way. But the reality we have in chemistry is that if we have data, so far it's mostly in the form of some fuzzy kind of text. So if we look at colors of compounds, for instance, we just have like something blue, reddish, violet, pink. And so at some point we just took all the colors you could find for compounds in literature and then asked people what they see as this color name. So you take all color names from papers and the databases. So it might be something like red-brown, deep yellow, or buff. And we then just ask people at EPFL to take our app here and then just rate what they see if we tell them this name. And you see the response here. So for some colors, it might be still okay. But for some of them, we have an immense spread because people just don't even know what a name probably means. So here they just randomly guess. And in the end, this is what we do here in chemistry. We just have data in this messy form where we just have a big noise in the data in the end, limiting us what we can then learn with our models. Because in the end, our model couldn't be better than what the noise in here is in the data itself, because the chemists just don't agree what they actually see with those color names. So what do we do in this case here to make it better? In this case, it's a nice solution. It's easy to show because we can just like get a chatbot, a Telegram bot or something, and take a photo with a calibration card. And then we have a tool that then takes this image, then finds the compounds in there, calibrates the color. And in the end, we actually have numbers to look at, not only just some text, and put this all on the database in here. If you want to have a name, we also have a way to then get the name in the end, to put into your paper or to tweet about it. But in the end, the important thing is you have everything now in numbers in a database in a much nicer form. And in the end, it's still easy to use for a chemist because you just have to have your phone, take a photo of the compound on the lab bench, and you have a now way more efficient way and more practical way of comparing now, for instance, colors. And it's like the philosophy we had with ChemInfo, make it easy for chemists to use the ELN and then still have some kind of something that they in the end get out of using the lab notebook. Because in the end, if you have data in a structured form, you can do many things with this. So this is now a screenshot of the ELN we have. So if you have in there like Raman spectra, IR spectra, they are all in the same JChem format in this case in a database. You can of course load all of them into your ELN. You can then apply different techniques in it like PCA or clustering, and this all happens on the fly in a browser. And you no longer have to go to Excel or Origin or whatever tool you might have to get those analysis. You can just use the ELN and have all of this directly at your fingertips just from your lab notebook. And it's something we try to do for this ELN is to have both a carrot approach to give something to a chemist that you can really have from using this ELN, something they couldn't do before that easily, but also a stick by forcing them in some way also to use it. So we have this approach of having both a carrot and a stick for this ELN use. And in the end, if they use it, they also have a button in there, export to Zenodo. And so in the end, they can have a dump of all data on Zenodo, and then also have an Explorer there. So if you click on a link, there you will have Explorer, for instance, for this paper, where you have all the images in there, the spectra in there, and still all interactive, all alive. You can download the data and then still play with it and reuse it in an efficient way. And you no longer have just to rely on those different color names, for instance. And you can, of course, also get this further into teaching, for instance. So we just use those tools, for instance, here to also link to DFT simulations. So if you now have a compound, for instance, a moth, you can put it into a simulation workflow, like AIDA Lab, which is our simulation workflow engine, and for DFT workflows, but also GCMC for gas adsorption simulations, for instance. We can take this CIF file from XRD, for instance, put into AIDA Lab via the REST API there. And then you have different checks to see if the structure makes sense for simulations, like we check if the solvent is still there or not, if you have missing hydrogens or whatever. And then we have robust default workflows there for important simulations, like doing a geo-opt, getting the isotherm. And then after some time, you have the results back in your ELN. You can compare now simulation results with what you have in the lab. So you can really now have routinely a comparison between the lab results, between your lab isotherm, and what you then did with simulations. So you can, because in the end, an isotherm means nothing without a reference from the ideal crystal. And so having this reference here from simulation is really important, and now you can do this routinely without asking your friend in the simulation group all the time to do this for you. We can even go further with this to teaching, for instance. And what we did here is we used the same tools here to build like a lab for students to play around to learn how IR spectroscopy works. So often you just have those tables in books linking like this band here occurs at this wave number, and therefore it's like a carbonyl or something. But what we have is we have now a drawer here. You can just draw a compound and then get on-the-fly predictions with just XTB simulation, in this case here, of the spectrum. And then it's all interactive. You can click on different bands. You see the animation of the vibration of the mode. And it's also linked across, like if you can click here on a bond, you see the mode appearing here. So really now a nice way of interactively exploring a concept which you couldn't explore easily before, with those tools that are all just in the browser without installing anything at all. We also have some examples you can load. So if you want to look at like electronic effects, like inductive effects, mesomeric effects, we all have also libraries for this to explore those things in a comparative way in this ELN. And but in the end, many of those things are still in text form in there. So if you look at data, we have some fields in it to structure it, but in the end, this is a screenshot from the reaction view, you still have this text field in there. Because in the end, chemists love to have text for their reactions, because it's often just very flexible to record things. Because you often do novel things, you do a novel step in a reaction, you have a new stirring step, a shaking step, that then changes what you see in the end. And often there might be no field for this in the table. And so how do you now leverage this information in a more flexible way? And text is a very flexible way. You can just record in text. I now shake it for 10 seconds, and then I put it into my new machine where there's no field in the database. But you can put all of this in text, but you couldn't put it in the database without having some specialized fields in there. So the question is how you leverage all this text. And with this, we just think of prediction in chemistry as text completion. So we have here different compositions of alloys, high entropy alloys, and we want to know what phase they will form. If they form one phase or many different phases. We want to map composition to if you form a single phase or different phases. And so in this case, we just form different prompts and questions of this, and we have the answers. In this case, we just have the question, what is the phase of this alloy? And then the thing we do is we just take an LLM, a large language model, and then fine-tune this language model to be better at answering those questions, to be better at answering correctly what the phase of this composition is. And we end up in the end with a new language model that's better at answering those questions. We can then take this new model, this new LLM, ask new questions, and get new answers out of this model. In this case, we just use 0 and 1 to encode the different answers like single phase, multiple phase. And the interesting thing is that this works quite well across the board. So if you look at now this case here with those alloys, we have here learning curves, but we have the accuracy. It's a balanced classification case, so accuracy makes sense here as a function of the training points. We start with 10 points here and have different curves on here. We have a dashed line from domain experts, the people who know what they do, in contrast to me. So they really build like with thousands of points, features, and engineer a model there, and they have this dashed line here. And we have AutoML from Berkeley Lab shown in green, which is this learning curve here. And we also have from Taylor Sparks group CrabNet, transformer based on compositions, and it's shown in the other curve here. And then we have in blue this naive approach, just fine-tuning a big LLM, and we beat the domain baseline with really experts who know what they do as feature engineering here with just 50 points here. And it's happened across chemical space for different materials, from reactions, molecules to materials for different kinds of tasks, classification, regression, and inverse design. We often have quite surprisingly good results with just doing this naive approach of fine-tuning an LLM. So if you go just back to my thesis, if you go to the polymers, we have here a model in green built over weeks, fine-tuning features by hand, thinking of like what makes sense to a model, and then you get this green curve here. And then you just put the monomer sequence into an LLM, fine-tune it, and we get the blue curve here. And I could be way faster in my PhD by just using this blue approach in contrast to this week-long green approach here. The same with oxidation states. We have those fancy models based on atom environments, trained on, in this case, 10,000 of points for each of them. We take just composition here and fine-tune this LLM, and we again are quite close to what we have gotten before with way less effort. So those models can really give us a new way of dealing with data in chemistry, but you don't have to trust them, luckily. So if you don't trust them, you can just let them use different other tools. And this is shown here. So you can give a model access to a list of different APIs. It might be the ELN API for simulation engine, might be an RDKit web service. And then the model will parse your question in English and then go through those APIs, look what fits to your question, call this API with the right inputs, get the answer back, and then think if it's done or if it has to still call another API, and does this until it has the final answer for you to show you in Markdown, perhaps. So you can, in this case, for instance, you have to first look up what the common name means, go from common name to smiles, then call from smiles to conformers, then go from conformer to a DFT simulation workflow, and then in the end, convert the units with something else. And luckily, you can then still see what the model has done because we have this button here, which says Advanced Logs, which will show all the steps the model went through. So you have still full introspection from all the steps what the model has been thinking about and what the model has caught with which inputs. You don't have no longer a black box. It's really something you can look into what happened across the full chain of using different tools. So you really have a novel way of interacting with tools, making them more accessible, but also having workflows just being developed on the fly and by letting the model choose which tools to use. And in the end, the nice thing is you can also incorporate the hybrid model quite well in there. This is something relatively recent. So here we want to know if you have different polymers, they form different shapes. If you mix them, depending on the monomer ratio in there, they might form spheres or different worms. And it's often hard to know a priori what will happen, but chemists have some rules of thumb. So they know if I see those things in some cheap measurement, I will probably have a sphere or a worm. But if you just take those rules of thumb chemists have, you're quite bad. So it's this here, just the rules of thumb. And if you just use the model alone, you're still not good. But with the LLM, you can put into the context of the model, into a prompt itself, those rules of thumb, and then use the best of both worlds in some sense, and then get the best performance in this way. And the important thing is you can put just like this fuzzy into the division you have here. That if one thing is high, you don't even know the number, don't know the threshold, you know it's only if it's high, put it into a prompt as just text, as English text, and the model can reason about this, which you couldn't do before. And so I think this really gives us a novel way of using the same approach for different chemistries, making stuff way more accessible, incorporate a lot of context in there, and reduce the barriers for modeling and for using those tools by quite a bit. And so we now push this further because most LLMs so far don't know chemistry, so they're just trained on the internet. So we currently train a big foundation model for chemistry. So we're collecting a big data set here with OpenBiome and Stability AI, and currently have the first runs of training a big model focused on chemistry data. We have journal articles in there, ChemArchive, BioArchive, and so on, and also a lot of structured data from tables, which convert them into prompts to then train this model there. And so I think we now have a lot of the tools in place. We didn't mention all of them, but we have also like tools focused, for instance, just on MOFs that really helped us then address problems across scales, from the atom scale to the plant scale. And luckily, I had a chance to do this with a great team at EPFL and across the globe, mostly with Luc Patini for the ELN part, and for the MOF part with folks in Berkeley. Now I'm lucky to have a small team in Jena who will focus a lot on doing LLM stuff. And I hope that together as a team, and if you want to join, you can still apply. I'm still hiring. And look for materials with our digital agents to have a more sustainable future together. Thank you.